we start, just some kind of updates on a little bit where the class is headed and what the plan is, at least for the next couple weeks. So obviously we have class today, we have class 2 times next week. If you looked ahead at the syllabus, you would notice there is something, it's called an intro report on the syllabus. Probably haven't seen it, but it's supposed to be due Wednesday. Because we've missed a couple days of class this semester, that's going to be pushed back till after spring break. So on Monday, I'm going to introduce what in the world we're doing, but the intro report part won't be due until after spring break. So we're going to have a group project coming up. We'll talk about it Monday. The only thing you're going to do before spring break is tell me if you have a specific person in mind from the class that you would like to work with. Otherwise, I will form teams. So they'll be like, we'll try to get teams sorted out before spring break, but there's not going to be any stuff happening before spring break. For that, there is one final assignment before spring break, so that will be due Wednesday. It's like a mini assignment, hopefully at least. It's 3 problems. 2 of them should be pretty straightforward and easy. One shouldn't be too bad. We'll see, I guess. It shouldn't be bad. All 3 of them are using Bernoulli's equation. So it's just to try to get some kind of light practice before spring break, figuring out how that works and how we can basically use that, right, as sort of like an energy balance. To say the energy of the fluid at one place equals the energy at another place equals the energy at another place. So we'll do that. That's that homework assignment is posted now. So you have enough stuff. You can work on it over this weekend. You can work on it next week, but that's going to be due on Wednesday. Last kind of general note. So my wife is pregnant and expecting a child kind of at the end of March. So the current plan is that I am going to be here up like until spring break, and then I will not be here directly after spring break. So the classes, like right when you come back from spring break, I won't be here that Monday. So Dr. Veldman is going to be coming and filling in for a couple class periods while I'm not here. So I'll come back like probably after Easter, and then pick back up with kind of where we've left off and what we've covered. I'll make sure at least one of you I might bug to try to get your notes from the couple classes that I'm not here, so that I make sure like I know exactly what you've covered and how you've covered it. So I'm not asking things on an exam that like, oh, I thought you would have covered that and you didn't. So I'll make sure that I catch up with where you guys are at and what you've covered. So hopefully that transition, like me gone, me coming back, hopefully works pretty smoothly. But just know that's coming up after spring break. Last thing, I did not get a chance to get exams graded by today. We had a lovely problem with our sewer backing up into the basement this week. So that was what my night consisted of. It was a lot of fun, even more fun than exams, in fact. So I'll get them back for sure Monday. They're almost done. So we'll have them back Monday, but unfortunately not today. So you get to celebrate one more weekend, I guess. All right. So what we're going to do today is something that for many of you, this is probably like the only time that you're ever going to do this, but I think it's fun enough that we're going to do it. For some of you, you will see things like this again in real life. And for many of you, even if you never actually do this again by hand ever in your life, which again will be a lot of you, most of you will interact with computers that are doing this exact thing in the background. So what we're going to do on this handout, this is what we're going to work with today. Basically, we're going to take and transition from dealing with things that don't have viscosity to dealing with things that do have viscosity. And we're going to kind of go through and look at how the Navier-Stokes equations can give us a predicted flow pattern. So this is, again, the same basic thing that you would do, like if you're modeling airflow over an airplane wing or over a car, or like you're modeling Even if you're mounting like stresses in a beam, say if you're like designing a civil structure, something like that. A lot of kind of the basics are going to be really the same. Usually for most of you, this is stuff that's going to happen in the background with some software package. But I think it's interesting to kind of see, like, what we did is we built this whole system of equations by basically trying to apply F equals ma to a fluid particle. And what this is going to allow us to do is then predict if a force is applied, what's the fluid going to do? And we're going to be able to then like take this, system of equations that we built by saying F equals ma, how does that work to a fluid particle, and then be able to predict flow patterns, which is going to be kind of cool. I think it's cool, at least cool enough that you should at least see it once, even if we don't really do a whole lot with it in this class. So what we're going to do, we'll kind of go pretty quickly through this. We'll see, Jack, you want to maybe come up and grab one of these sheets before you sit down? All right, so this is switching us really from chapter 7 to chapter 8. So in chapter 7, don't do this to your paper, but what we said in chapter 7 was, sorry, not chapter 7, what we said in chapter 6, when we did like Bernoulli's equation and figured out, how, streamlines curve away from pressure, things speed up as they move toward pressure. You have kind of this balance between pressure and height and velocity because your total energy stays constant. All of that stuff came really from this equation where we said viscosity was 0. So it crossed out all of that stuff. So the only 3 things we had acceleration, which is that part, gravity, and pressure, which is why in like Bernoulli's equation, the only 3 things we had were like kinetic energy term, velocity, pressure, gravity. So that's where that came from. What we're going to do here is there are a lot of systems that's pretty useful. We did some of them, you'll do some more in the homework, but that's not useful everywhere. A lot of times, like the viscous forces, the viscosity of fluid actually matters. So that's what we're going to do here. We're going to let the viscosity be something other than 0 and see how that can help us to predict flow patterns. All right, so this is going to be, if we want to label this will be the start of chapter 8. Chapter 8 is mostly not going to be like what we're doing today. So it's going to kind of shift gears a little bit, especially after spring break. It's going to feel a little bit different. But what we're trying to do in chapter 8 is to predict internal, incompressible, can't spell, viscous flow. So internal meaning like inside of a pipe or inside of a channel or something like that. Incompressible, density is constant. And viscous flow means we have to care about viscosity. Viscosity is non-zero. All right. So that's governed by the Navier-Stokes equations. So let's kind of see a little bit how they can get us to predicted flow patterns. Okay, so what we're going to do is start with a diagram. So let's imagine a channel like this. So these are both solid walls. We have some gap between the walls. We'll call it B. We need to put axes onto our system. So let's call this Y. And down the channel X. And a system that we've looked at before is where like the bottom plate is stationary and the top plate is moving. So let's look at that. So let's say this top plate is moving with some speed, capital U. All right. And the bottom plate is stationary. So the Navier-Stokes equation should tell us exactly how the fluid moves in response to this. You probably already know, right? What is the flow going to look like? It's going to be 0 at the bottom. It's going to be capital U at the top, and it's going to be a straight line in between those two. So it's going to be a triangle. So we already know that, which is one of the reasons why we're doing this problem to start. So we know what the answer is going to be, but let's see how we can get from this really big, nasty thing to a solution that's as simple as like it's linear. So we're going to come up with some assumptions. Some are not really assumptions, but they're kind of like intuition about how the problem is going to have to work. And that will help us cross out terms in the Navier-Stokes equation, give us a simpler problem that then we can actually solve. So assumptions about the flow. So in which direction, just given your intuition of the system, in which direction is the fluid going to be moving? Going to be moving in only X. There is not going to be any component of motion in Y because we don't have anything pushing it in that direction. And there's not going to be any component in, we'll call this Z. There's not going to be anything pushing it that way, so it's not going to be moving that way. Like the only push is a shear at the top that's kind of pulling it along in X. So that's going to be our first one. Flow is only in the X direction. So maybe another way to write that. So our velocity field is going to have an X component, U, but then it's going to have 0 J component and 0 K component. All right. For the sake of simplicity, let's look at the system where things are not changing with time. Does that sound like more fun? So let's say that this is steady flow. So the change in the velocity field with time is equal to 0. Okay, what else? What can we say maybe about gravity? Which direction is gravity pointing, or which way do you want it to point? It's probably pointing down. Okay, so gravity is in Y. All right, so that means Gx equals 0 and G. So those two parts of it are both 0. Okay, the last one, this is again not really an assumption, but this is kind of an intuition thing. The flow is only changing. Okay, in which direction, X, Y, or Z, or maybe multiple, do we actually have like variations in velocity, changes in the flow? Y. So we're not going to have, if we go like in and out of the page, it's not going to change that direction. It's not going to change down the channel. It's only going to change as we go from the bottom wall to the top wall. So flow is only changing in Y. All right. So what we're going to do is cross out a whole bunch of stuff. So what I'm going to do, we're going to make things 0, but I'm going to do something. Well, we're going to go and use each of these 4 things to cross out different terms in the Navier-Stokes equation. So we'll do it with the first one. If the flow is only in the X direction, that means anywhere where we see a little V or a little W, we can cross it out because those are 0. So for example, like up here, that term is going to go to 0. What I'm going to do though is not just cross it off. I'm going to say why we crossed it off. So I'm going to say, like, we crossed that off. It goes to 0, but it goes to 0 because of what we said in 1, because of what we knew about the system. This next one also goes to 0 because of what we said in 1. Everything else is U's, so we can't do anything, but this guy does the Lord's work on part 2 and part 3, right? Like 0, 0, 0, 0, 0. These are second derivatives, but I don't care because the second derivative of 0 is just even more wonderfully 0. Down here at the bottom, we're doing derivatives of all sorts of things, but I don't care because they're all 0 because I know W is 0. So this guy crosses some stuff out of the first equation, but just, really mops up the second and third parts. Okay. Then steady flow. Anything changing with time, it's not changing with time. So this is the only thing left that's changing with time, the du dt, that top left term. So that's going to be 0. Right. If gravity is in y, we can cross out gx and gz. So gx, that gets crossed out because of 3, and gz, that gets crossed out because of 3. Okay, so we've now solved the third equation, right? We have to solve all 3 of these. So the solution of the third equation is everything got crossed out except the change in pressure. So then that must also be not changing. So the answer is nothing is changing in Z. Done, solved it. Okay, we kind of solved the second one too. That one, the only things left are gravity and pressure. So this is like a fluid statics problem. So how does pressure change in the y direction? Well, it changes because of like gravity. So there's a slight pressure gradient in y because like it gets a little deeper. We can figure out what that was. Not super interesting. So solutions to so we've solved 2 of our 3 partial differentials. We're not yet done with the first one though. So let's use our number 4 kind of assumption or description of what's happening. So if the flow is only changing in y, that means the change in x, or the derivative in x, must be 0. Second derivative must also be 0. And if we look at changes in z, those are also 0. So let's look back up at our top equation. So this term here, the last thing remaining on the left-hand side, has to be 0 because that's talking about the change in x, and we said things are not changing in x. And these 2 must be 0. And the pressure is also not changing in x. So we only have anything changing in y. So we crossed off everything on that top equation except one thing. And this is how you get analytical solutions of these big equations. You cross out everything interesting, and you're only left with like super simple stuff. Okay, but let's see what happens. So let's write our simplified equation. Our simplified equation is 0 equals mu d squared u dy squared. So that's the only one we haven't solved yet. We've solved the other 2. Z is nothing's changing in Z. Y is pressure changes with depth, how we've done before. So this is the only part that we need to solve yet. To solve it, though, we need 2 pieces of information. So we have, this is the governing equation, but we need something describing what happens at the boundaries. So we have differential equation, we need 2 boundary conditions. What do you know about what must be happening at the boundaries in our system? Yep, I agree exactly. Those are the boundary conditions we'll use. You know that because of the no slip condition. So that's like kind of a weird thing, right? The fluid, you said it can't slip across the surface. We watched a video where we saw that that's true. It's not like a really provable thing, but it's an experimentally verified, like you can watch it and it doesn't happen. So we have our two boundary conditions. Both of these are really a result of no slip. And as Jack said, so we have the velocity, let's write it this way, evaluated at y equals 0. So at the bottom, we are moving with the speed of the bottom plate, which is 0. And at the top, at B, we are moving at the speed of the top plate, which is what we've called capital U. So that's our math problem that we actually have to solve now. So let's flip over and we'll go about solving that. So flip over to the back page and we'll do a solution. So we're going to solve for the velocity field. We have our equation. Right, we have our equation, so let's integrate it and solve it. The 0 can cancel out our viscosity, so d squared u dy squared. Then we can sort of multiply both sides by dy and integrate. So we have du equals 0 dy. What is the integral of 0? A constant, something we don't know, but so sorry, this should be du dy. So du, can't write, du dy, we'll call that constant C1. We'll do the same thing. We'll multiply both sides by dy and then integrate. So we have du equals C1 dy. Then we'll integrate both sides and get u equals C1 times y. And then we get a new constant integration. Now to figure out what those constants are, we have to apply boundary conditions. You can see already that's a linear equation, like y equals mx plus b. So we know we are supposed to have a linear velocity profile. We do. We just are proving that that's true. So to apply our boundary conditions, so the first one is that at the bottom, our fluid is not moving. So if we plug in 0 for y, we should get 0. So this one should give us 0 equals C1 times 0 plus C2, which tells us that C2 has to equal 0. So we've solved for our first constant. And then we can apply our second boundary condition. So at the other side, at B, our velocity equals capital U, the speed of the top plate. So let's plug in and solve. So this tells us that capital U equals C1 times B plus C2, but C2 we already found was 0. So this tells us C1 is capital U over B. So our velocity field is capital U over B y I hat. Which if we drew this, if you want to flip it over and draw it on your other side, flip it over and draw this. Let me get a little bit thicker line. Right, this is going to be exactly what we knew already at the start it was going to be. Now we've proven that that has to be true. Okay, so that's how we know that that's going to be the velocity profile. It's a result of how forces are being applied to the fluid. Okay, let's do one more that's a little bit more interesting. So flip over to the next page. It's going to be similar, but a little different. So this one, we're going to have a different force that's causing fluid motion. So we're going to have the same geometry. So we're still going to have a channel. We're still going to have this be y, that way be x, and in and out be z. Our channel is still going to have a width that we'll call b. But this time we're going to have our walls stationary, and what's going to be pushing our fluid is pressure. So instead of like the wall dragging the fluid along, we're going to let pressure push it. So we're going to have this be a higher pressure, and that be a lower pressure, and that's going to cause the fluid to get pushed down the channel and flow down the channel. Okay. So let's do, it's kind of the same thing. We'll write out what we can figure out about how this flow has to behave, cross out a whole bunch of terms, hopefully end up with a simple enough problem that we can solve it. Hopefully we can solve it in like 20 minutes. All right, so we can use a lot of the same basic reasoning that we did in the last problem. So we're still going to have flow that only is in x, because that's the way our forces are pushing it. So we're only getting pushed in x, so that's the only direction that we're going to be moving in. So our flow is only in x. So this is little v equals 0 and little w equals 0. Okay, we're going to look at the steady flow version of this. So that's the time derivative is 0. Gravity, let's say it's still operating in y. So gx and gz are 0 because gravity is in y, it's say pointing down. And then we know kind of two other things, and these are sort of linked. We know that pressure is changing in x because that's what's pushing our fluid. But our velocity is changing in which dimension? It is going to be changing in y. It's going to be fastest in the middle, and it's going to change as we go up and down across the channel, not in and out of the board, not down the channel. It's not going to change. It's going to change up and down. So, all right. So let's use these guys to cross out a whole bunch of stuff and hopefully end up with a simple problem. So the flow is only in the x direction. Everywhere we see a little v or a little w, we get to cross it out. So let's go to town. That's a little v, so that gets crossed out. That's a little w, so that gets crossed out. Nothing else in the first term. But then this crosses out basically all of the second and third terms again. Right? That guy gets crossed out. That guy gets crossed out. That guy gets crossed out. And same on the bottom one. All right. Next one, steady flow. If we have steady flow, changes with time are 0. So there's one last lonely time thing. So he gets to be 0. If gravity is in y, then that's our third one. Gravity is in y. We get to cross out the other g's. So this guy is 0, and that guy is 0. So we end up with the same solution to the equation 2 and 3. Like equation 2, there are pressure changes in y just related to the depth. Equation number 3, nothing is happening in z. Nothing is changing as you go in z. Done. Solve 2 of the 3. We still have a little bit of work to do to simplify the top one. So let's do our last thing, number 4. So if we have pressure changing in x, then we can't cross out. Then we have to leave this guy alone. So he's going to stay. If we know our velocity is changing in y, we can cross out the changes in any other dimension. So if the second derivative of x must also be 0, because if it's not changing in x, then it's not, the second derivative is also 0. Same with this guy. He's got to be 0. So we're left with a little bit more complicated, but still not too bad problem. So we have 0 equals minus dp dx plus mu d squared u dy squared. Okay, we need boundary conditions to solve this. So what is happening at the boundaries of the system? So it's 0 at the bottom and it's 0 at the top. Those are the two boundaries. No slip condition. It's got to be 0 both places. So those are our two boundary conditions. So again, we're going to use the no slip. So boundary condition 1, little u at 0 equals 0, and boundary condition 2, u at the other side at b has to be 0. So there's our math problem. All right, we do have one kind of funky thing, a little bit funky, and that's this first term here. So I'm going to put parentheses around it just to kind of indicate like this, we can kind of treat this as its own separate thing. So this is the pressure change in x. We're going to be integrating and doing stuff with respect to y. So we don't have to care about the pressure change in x. So as far as y is concerned, this is just a constant. So it's going to work and be treated, it's the pressure change in x, but it's going to be, we'll treat it just like a constant. Right, so this is just a constant in y. Right, so the pressure change in x from the bottom of the channel to the top of the channel, it doesn't matter. The x part of the pressure change isn't affected by where you are in the channel, top or bottom. Right, so that's what that's saying. Okay, so it's going to stay there. It's going to look kind of weird, but it's just going to be a number. So let's flip this over and do some math. Luckily, it's math that we've already done, so hopefully it kind of feels the same as what the last problem is. So it's 0, negative dp dx plus mu d squared u dy squared. Okay, so we're going to get the d squared u dy squared on one side, and we'll have 1 over mu minus dp dx. We'll keep that as kind of its own thing. Sorry, it lost its minus sign when it moved over to the other side. I'm doing my algebra wrong. So we move the dpdx over, that flips the sign, and then we divide by mu. We multiply by dy, multiply both sides by dy. That will be du dy equals 1 over mu dp dx times dy. Then we can integrate. This is just the integral of a constant. It's a funny looking constant, but that's a constant. So this is equal to 1 over mu dp dx times y plus a constant of integration. Okay. Do the same thing again, multiply both sides by dy and integrate. 1 over mu dp dx times y plus c1. And that whole shebang is now multiplied by dy. Then we can integrate this guy to find u. So we integrate this like in two pieces. So the integral of y with constant is like y squared over 2. So this is 1 over mu dp dx. Those are all constants. And this part turns into y squared over 2. And c1 is c1 times y. And we end up with a constant, c2. Right? We get rid of the constants by applying boundary conditions. So let's do that. That's fun. Cool. So it keeps erasing me. Let's see if we can get it to actually work.